All right, what do you think? Should we go ahead and get started? Hi, everybody. How are you all doing today? There's still quite a few of you here. I thought people would be sneaking away for Easter break early. So, how did the project go? Everybody get it in? Just kidding. I know. It's fun. All right, now that you're awake, I'm not going to say anything about this, but I found this website, drawyourprofessor.com. Okay. All right, I suck, and the reason I suck is because even though you haven't left early for vacation, I am actually leaving early for vacation, and I will not have office hours today. I'm taking my family to Disney by 7 p.m. tonight. We'll be at Disney World, so we're psyched. If you're 3- and 6-year-old boys, you are very excited. If you have problems, please email me. I'll have email or post on the project forum through Blackboard. I did subscribe to that, so I'll see things that you post. Okay? If you have immediate questions, catch me right after class. I can answer questions for a second. Other than that, last time we talked about a bunch of stuff. Anybody remember what it was? Linked lists. And in particular, what is a linked list? It's a self-referential data structure. It's a data structure that consists of objects, and inside the object is a link, which is a pointer to some other object of the same class. So each object has a pointer to some other object in the same class. So when we're looking at a linked list is literally the simplest one we can use, right? We have an object, it has one pointer that goes someplace else to another object, and I've hinted that in the future there are more complicated versions of these things, and part of what you will study if you can consider in computer science is what you can do with all this stuff. All right, what we were talking about in terms of linked lists last time was mostly a node and how to manipulate nodes to link them together, right? If you remember about nodes, they had two pieces inside. One, which were they? Anybody tell me what was inside a node? Sir? Some data, and what kind of data do we have inside a node? Okay, last time we had what? We had an int, but does it have to be an int? What else could it be besides an int? Those things. And you all see these things before. So what I'm talking about is when you're building your project, the pointer stuff is going to all be very similar to what we're doing here. Your class, when you make the refugee class, is going to be very similar to what we're doing here. All the pointer operations are going to be super similar. It's just the data inside the object is going to be different. I think I mentioned that last time. Everybody kind of understand that? So it's kind of like now we're throwing Coke bottles overboard and they just have Coke in them. But in the future, we're going to be throwing like bento boxes overboard and they have like compartments with a lot of stuff. Waterproof sinking bento boxes. All right. Then we also had the other thing in there, which was this. Anybody want to tell me what this means? Yes. It's the address of the next node, and the next node is of what type? A node. So when we see this, when you see node star, what does that star mean? We went over this. It's an address. This isn't a node, it's the address of a node. So anytime you see the star, that means it's an address. This is the address of a node, and we say that as, if we wanted to say this out loud, we say next node is an address of a node object, or next node is a pointer to a node object. So here, let's just talk about what we're going to do today, okay, and what I'm going to try and get through because it's all stuff that you would probably like to have for the project. What we're going to talk about is we're going to talk about a list class, The idea of the list class is that we have the nodes and we can see how they link together. The list class is going to be the class that we actually build the list out of nodes. So we'll have a list class that has a pointer to the first node, and then we'll have, and it looks like this. We'll have a pointer to the first node, which is the head, because traditionally the pointer to the first node on the list is called the head pointer. So we're going to have that in our class, and then we're going to have some methods. And the methods are going to allow us to operate on the linked list. And it's going to allow us to do stuff that we want to do with the linked list. What might we want to do with the linked list? Anybody want to guess? Yes, sir. We might want to add a node. Okay, we might want to add a node to the linked list. And so we're going to talk about adding a node to the linked list. You probably can't hear on the recording, but your answer was add a node to the end. Which, the far end or the front end? Which end? Okay, so you can do it you can add a node to the far end, or you can add a node to the front end. You could add it in the middle if you wanted. You can do whatever you want. It's your linked list. How many of you want to do it like a hard way? How many of you want to do it an easy way? All right, so we're going to do it the easy way, which is actually adding the node to the front of the list instead of at the end. If we have time, I'll show you how to add at the end too, because that can be useful. We're going to talk about search. Why might you want to have a search method? And so you can find things on the list, absolutely, right? You have a list. Search essentially allows you to search through the list and find things on it. More importantly, what it shows you is how to iterate through the list, right? Now, do you all remember, it probably seems like months ago now, we were working with something called vectors. Everybody remember vectors? And we had one thing that showed up all the time we wanted to look through a vector. And what was that? A for loop for n I equals 0, I less than vector.size, I plus plus, right? And then you could use the square brackets. So we used that all the time, didn't we? For lots of stuff. What we're going to talk about today is how to do the equivalent operation on a linked list and how to iterate through a linked list, okay? Now, iteration is useful in other cases beyond search. For example, anybody know what this is? Tilde list, yes? This is the deconstructor. And this is what deconstructs the object when we're done. I'm sorry, destructor. That's not even spelled right, is it? That's the desk true. Okay, so whatever it is, we're going to delete the list when we're done with it. And it turns out, and I'll talk to you about this a bit more, is that when you get an object using new, and you have a pointer to it, that object never goes out of scope. Never goes out of scope. Normally when a variable goes out of scope, what does it do? It goes away and we don't have to worry about it. But when you use new, when you use the new command, it gets some memory and it holds on to it forever until your program finishes. So if you don't explicitly get rid of it, it ends up hanging around. And this is a problem. It's a problem because over time, if your program is creating lots of new things and not deleting them, then the memory fills up and then your program starts to crash because it doesn't have enough memory. And I'll tell you some scary stories about this after that. Hi. So let's go ahead and get started doing all this stuff because it's going to be fun. So what I've done is I've created a new program. It's called list.cc. It has the node class in it. So we're going to be able to refer to nodes. And now what we're going to do is we're going to start writing a new class that is the list class. Oops. And we talked about some of the stuff we're going to have in here. What is the private portion of this list class going to have? If we're going to be keeping track of things on a linked list. And I will say I do have a very special prize today for somebody who answers a question. A miniature bottle of Tabasco sauce. So you can let me know if you're ready for a challenge question. All right, so what is the private portion of this going to be? I already told you earlier in the slides. The what? It's going to be, we're going to have a linked list that consists of nodes. And how do we keep track of where that linked list is? With the head pointer, yep. So we're going to have node star head. And what does this mean when you see node star head? It is the address of a node, and we're calling this head, and we're going to keep track of it as the head of our linked list. Now, we also need some methods to work with this. What methods do we need when we define a class in general? All right, constructor. So we'll need list. Actually, I'm going to make it capital. Sorry, just to be consistent. Okay, so we need list. It's going to be a constructor. Do you want to go ahead and write the constructor while we're talking about it? All right, let's go ahead and write it while we're talking about it. So this belongs to the list class. It is the list constructor. It takes no arguments. What do we have to do inside here to initialize things? Anything in particular? We only have one data member in there. Does that need to be initialized? How many of y'all think this needs to be initialized? How many think it does not? How many have no opinion and wish I would stop asking you questions? All right, here's the deal. Node star head, if we don't initialize it, what value does it get? We don't know, some random value. If you start following pointers to random places in memory, what happens to your program? It crashes. Do we need to initialize this head pointer? Yes. This is a very common error that people make when first working with pointers, is forgetting to initialize pointers. In general, you should always initialize pointers. It will help save you from problems. Yes, sir? Okay. All right, so we've got to make sure we initialize that. That's something that should absolutely be done in the constructor. Otherwise, bad things are going to happen. Okay. All right, what other things did we talk about that we wanted to have here? We wanted to have an add a node. And what argument is this going to take? It depends. We have our choice, right? I'm going to try and make this easy. I'm going to have it take an int, all right? And the reason I'm going to have it take an int is so that we can just build the node with the right int when we need it, instead of having to build the node and then give it to the list. So we can add a node and we can just say it's going to take an int because we know the node class right now takes ints. All right, should we write this one first? Or do you want to talk about the other ones we're going to do? Let's just write it. How about we just write it? So I'm going to draw a quick picture here on the board. We're going to have some head pointer. And when we start, what's it going to be pointing at? It's going to be initialized to point at nothing. This is the way that when I draw pictures, I draw it to mean that they're initialized pointing to nothing. It looks like a ground symbol instead of pointing at anything. Okay? How do we add a node to this list? Is this a list, by the way? Is this a linked list? Yes. It is an empty linked list. It is a linked list that contains 0 objects. So a pointer to a node is a linked list. It just happens to be an empty one, right? Like if you have a vector with nothing in it, is it a vector? Yes, yes it is. There's just nothing in it. This right here, when we say node star head and then we declare it head equals no, is an empty linked list. It is a perfectly valid list. So how do we add a node to this? We need to create a node that has a number in it, and then where do we put it? Where? Yep, so we create a new node, and then we're going to link this pointer to it, like that. When the list is empty, when we put the first node on, are we putting a node at the beginning or the end of the list? Both, all of the above, right? If there's only one node, we're putting it at the beginning and the end. So let's go ahead and start writing this class, and we can see how this works. All right, we're not going to return anything. Sorry, void add node. And we're going to take an int. And here's what we're going to do. We're going to say node star temp. We're creating a temporary node. Oh yeah, that would help. Node star temp equals what? How do we get a new node? New what? Node. Whoops. New node x. So here we have void. We return nothing. This method belongs to the list class. It's called add node. It takes as an argument an integer, which we named x. And the first step we're doing is we're creating a temporary node named a pointer to a, we're creating a pointer to a node called temp. Let me scroll this up where you can see it. That is equal to a new node x. So when you see node star temp, what does that mean? It's a pointer to a that's named, it's a pointer to a node that's named temp, and this is actually pointing at what? A newly created node that has as its value x. Yes, sir.
So
Nope, the pointer is named temp. What is the name of the node? It doesn't have a name. When you use new in general, and by general I mean always, it doesn't have a name. Okay? Everybody with me so far? Sir? And the value is x. So what we're going to say is we're going to be able to say, hey list, take 5 and add it to your list. And the list is going to go, okay, 5, create a new node with 5 in it, and we're going to add it to the list. And here's how we're going to add it to the list. We're going to create this new node. It's pointed to by temp. So let me step through with some pictures here. All right. So initially, head points to nothing. And then we create a new pointer called temp. And we point that in a new node, and it's going to have value x in here, and it's going to have next node in here. Or just next is what we called it. And when we initialize it, that pointer is not pointing at anything either. Okay? So when this gets called with the value x, the first thing that happens is this node is created. It's got x as its data value, next is nothing, and temp is pointing there. Now, here's how we add things to the list. What we do is we say temp arrow set next head. What does this line of code do? All right, I've got candy for this one. Almond Joy. Anybody? Yes, sir. Uh-huh. All right, so we go to temp, we follow the arrow, and when we get there, there's an object. And what do we do with this object? We call set next, and we set it equal to head. Okay, what is head right now? Null. Head is null. So it sets that to null. Okay? Now you might be asking yourself, why do you do that? I'll show you in 1 second. And now we say head equals temp. So what we're essentially doing is, think of it this way. We have our line of fishing line and Coke bottles that we've thrown over the side, right? What we're doing, we want to add a new bottle, is where we're taking the string from the new bottle, we're hooking the old string that was hanging off the side of the boat to the Coke bottle and throwing the whole thing overboard. So we're adding things to the front of the list, all right? So what happens is, initially, this thing is created. Then what we do is we set this to point at what head pointed at, and now we switch head to also point at temp. Now, this time is a little bit confusing, okay? Because this is the case where there's nothing on the list. Let's do it one more time, okay? Let's say we're adding one more node, and we get add node gets called again, and everything looks like that. What happens now? Let's step through the code and see. What's the first thing that happens? We create a new node. We store its address in temp. And it's got some new x value in it. The next node inside of it points at null, because that's the way the constructor does. So this one line of code there, node star temp equals new node x, creates a node. It stores its address in the pointer name temp, and that line of code is done. Okay? Everybody with me so far? All right, this next step, temp arrow set next head, what does this do? Sir? Uh-huh. Yeah, so here's what happens. We go to temp, we follow the arrow and we reach an object. When we get to that object, what method do we call? Set next. And what do we set it to? Head. We're setting it to head, right? So follow the arrow, set next, and we set it to head. This changes this pointer in here to point at whatever head is pointing at. They have the same address. Okay? Now, what's the next line do? Head equals temp. So this pointer that was pointing at the lit object before now points down there. And you can see, right, this new X we put on there is now the first thing on the list. If we start at head and we follow it, here's our new one, there's the next one. So this adds nodes to the head of the list every single time. It just pushes things onto the head of the list. Should we do it one more time just for fun? We're going to step through this again. Okay? So, who wants to walk me through it for a Milky Way bar? Milky Way? No? Bottle of Tabasco sauce? Tabasco sauce? For your Almond Joy bar? No? Nobody wants anything? Come on. Class is almost over. It's going to be break. You can have Nestle Crunch. Yeah, we're going to step through this one more time. Who wants to step through it with me? We just saw what happened. Okay, Julia. Okay, so the first line, new node temp creates a new node. And what pointer is in this one right now when it's created? Yeah. All right, so that line creates a new node. The address is stored in temp. Then what happens? Okay, so we start at temp and we follow the arrow. This delivers us to this object here, which is a node. We call the setNext method on it, and we set that equal to head. So this switches this pointer here from null to point at what head is pointing at. Okay, and now what? And now we change what head points to, and now it points at what temp points at, and this new thing was again put on the front of the list. Okay, everybody see how that's happening? If you see how it's happening, raise your hands. Any questions? Tabasco sauce or crunch or both? Okay. Yes? Okay, when did we create head? Yeah, so head, this thing head, is actually this pointer that's the private data member inside the list object. Okay? So it's a pointer. It's not a node, it's a pointer. It just is able to hold an address. Yes, in project 5, instead of having node star head, you're going to have refugee star head, if that's what you choose to use. Okay? Yes? Okay, if you didn't have head equals temp at the end, what would happen is the list would never get linked up properly, right? Because what would happen is you'd have temp pointing at this and head pointing over there, and so you'd kind of have something that's not quite a list. Yeah, it's like in some sort of indeterminate in-between form. Okay. Yes? The X is a variable name. I just drew it that way instead of using actual numbers. I'm going to show you an example of this in just a minute. But yeah, so I just use X to indicate whatever random number that people are putting in there. All right, it would actually be a value like 5 or 15 or something. Okay. So, yes? Because this is actually part of the list class, right? So add node is a method as part of the list class, list : Anything that has list : in front of it will be able to access the private data members. Okay? You couldn't do it from outside the class. Yes? So the question is, in project 5, when you do add refugee, would it be like this? So it can be like this. I'll tell you what I did for mine, which I think will become apparent if you look at the project 5 code. I created an add node class, an add refugee class that looks very much like this, but I made it a private data member so that I could call it from other methods within the class to add whenever I wanted to add something. Okay. Yes, sir. Yes, in fact, you are required to use friend functions in Project 5. So that is part of the requirements. All right, so this code right here is how you add something to the head of the list. Okay? How you add something to the head of the list. Yes? No. What's going to happen in the refugee class is the refugee class is going to look almost exactly like the node class, except this portion here where it says private, instead of having int data, we'll have string first name, string last name, int unsigned int age, char gender, and string camp. All of the data will be together in one. The refugee will be one lump together. Does that make sense? Instead of like scattered across things. So if you want to do add refugee, you could do add, there's a bunch of different ways you could do it. The way I did it, I actually did add refugee that took a refugee object as a parameter, which is slightly different than what we're doing here. And that just means that this step is different. So, okay. We can write it the other way if we have time. Okay, let's do it. All right. So the weird thing about teaching this is I've shown you how to add things to a list, but the only way you can actually believe that this is what's going on is by me drawing pictures on the board, right? So let's do something else. How about we do something that I forgot to put in my notes? How about we do something called print list? Would you like to be able to print out the list and see what's on there? Okay, and we'll do this, and we'll do print list, and then we can actually create a whole bunch of stuff. So this is going to be void. It belongs to the list class. It's a method named print list. Takes no arguments. And here's what print list is going to do. When we're given a list, and I'm going to redraw this picture. I kind of wish this classroom had more board space, but we get what we get. Here's what we're going to look like. Here's what our list is like. We're going to have something that looks like this, head. And it's going to point at some list that has a bunch of these things on it. Okay? And this is our diagram. So we have this head pointer. It points at a node. This node points at a node. This node points at a node. This node points at nothing. All right? So when we print this, what we're going to have to do is we're going to have a pointer that follows each step all the way down the list. Okay? So what we're going to do is we're going to say, okay, we're going to set a pointer here. After we print it, move it. After we print it, move it. After we print it, move it. So here's what we're going to do. We're going to create a temp pointer, and we're going to set it equal to head. We're going to use it to print the node, and then after we do that, we're going to set temp to point at whatever the pointer in this node points to next. Everybody with me? So here's what we need. We need a pointer to a node, node star. We're going to call this temp. And what does this equal? What value do we give this initially? Head, because we want this pointer to point to the same address that's in head. Check something really fast. All right, I didn't write friend functions for the node thing here, so what we're going to do instead is we're going to say cout angle temp get data. But you could also potentially do this. Okay. And what this says is it says dereference temp when you get there, output it, but you need friend functions for it to work that way. You should be able to do something similar to this in your project. Sir? Because it's an easier notation. It's a programming convenience. You could, the reason you don't just do dot like temp dot is because what is temp? Is temp an object or is it a pointer to an object? You can't call dot on a pointer. You actually have to follow the pointer to the object to call dot on it, to use a method like that. That's why we use the arrow. So the arrow is the equivalent of star in front of it and dot after it, which means dereference it and then call the method on it. It's just a more convenient notation. Okay? Because otherwise you got to do some ugly stuff. All right, so if we do this, if we say temp, node star temp equals head, see out, get data, this will print one node and one node only. What node will it print out? The first one. So what do we need to do? Yes? Yeah, but we need a loop of some kind, don't we? Because we're going to be doing this over and over again. Let's think about our loops. How many times are we going to be doing this? We don't know. If we don't know exactly how many times we're going to be doing it, exactly. So we're going to say, and here's pretty much the while loop we use for anything, while temp does not equal what? Null, which means while we are not pointing at an empty object, we see that out. We see out what the data is. And then how do we set temp to point at the next thing on the list? Yeah? Temp arrow. God, I hope I've been using the right. Yeah, set next. Oops. Yep, get next. So this, let's compile this and see if it works, okay? Because I haven't checked it in a while and I'm getting a little nervous about that. That's like I'm Neo. Look at that. Okay. All right. So this is the type of loop that you're going to use for everything. All right. You get a temporary pointer. You set it equal to what head is, and then you loop across the list. Each time you say, if we have not run off the end of the list, and if temp is not equal to null, then we can go ahead and process things. All right. So let's do a couple of tests of this and just make sure this works. So what we're going to do down here in main is we're going to say we have a list. And we can just call it, let's call it lowercase list. Okay. And we can do something like list.add node. Anybody have a favorite integer? 13. Anybody else? Favorite integer? I heard a 6. Anyone else? All right, so we're adding all these nodes to the list, and then we're gonna print the list. So we say list dot print list. Was that what we called it? Yep. Okay. All right, let's compile this and see if it works. I like colons. All right. Do you think this is going to work? When I run this, what is this going to print out? All right, so the first guess was 13,100, 623. That was quickly corrected to 23,6,113. Why did you correct that? Yep, because when you add a node, it adds it to the front, not the back. So when we traverse the list from front to back, everything should be in the opposite order. And indeed, that's what we see, 23,6,113. This loop right here where we say while temp does not equal null, do stuff, is what we're going to use for everything. This is the equivalent of the for I equals 0, I less than size of a vector. Okay? You have while temp, you get node temp equals head, while temp is not equal to null, and then you say temp equal temp get next. We use that very often. Yes, sir? Yeah. So if you want, we probably don't really have time because I'm trying to get through a lot of stuff today. This node class, we didn't write a friend function. If we wrote a friend function for it, like you will do for your refugee, you can just do output star temp. That means go to that, take temp, dereference it, which means go to the object there, then print that out. But since we didn't write the friend function, I just called the get data. Now, do you want me to show you a horrible mistake people make? A very horrible mistake people make? Okay. I'm going to create something called print list wrong because I will show you the wrong thing that people do. So we have print list wrong. And here's what people do. Wrong. The wrong way to do this is to just use the head pointer. Okay? Now, why is this wrong? Anybody want to guess? Yes. We did initialize head to null, but we added things to head when we did add nodes. So head was null, but now it's pointing at stuff. Does that create any problems? Yes. When we're adding, that's what we use temp for. Yes. Okay, here's our problem, which was summarized very nicely, which is if we change the value of head and we move head down the list, how do we get back to these earlier nodes? You cannot. You cannot. If we have no temp, if we have something like this, and what we do is we say, oh, we do this, and then we move temp there, and then we get rid of this, and we do temp there, head there, and get rid of that, and we do head there, we end up, how do we get to this first node? You cannot. What happened to it? It's gone. How long is it gone for? Forever. If you have a node like this, or a refugee object in your project like this, that you have no pointer to, it is lost. It's gone forever. This is called a memory leak. Okay? It's called a memory leak. It's kind of like if we had our bottles of Coke, right? And you took the string off the first bottle of Coke and attached it to the second, and then took that and attached it to the third. What happened to the first two? They fell overboard into the water and they are gone forever. All right, so this is the wrong way to do it. In fact, let's prove that it's wrong. Here's what we're going to do. We're going to print the list. We're going to print the list the wrong way. And then we're going to print the list again to see what's there, okay? Everybody ready for this? In fact, I need to put some output here so we know what's going on. So we're going to print the list. We should see 23,613 like we saw before. We're going to print it wrong. Anybody want to guess what we're going to see when we print it wrong? 23,613, and then we're going to print it again, and what did we get this last time? It's not going to have anything, because all the stuff is going to be lost. Print. What did I screw up? What? Oh, thank you. I took out the method prototype. All right. What? Come on. You let me do that and didn't tell me. Here, you can have the Tabasco sauce. So, all right. That's the prize. Okay, so let's see what happens now. We print the list, 23,613. We print it wrong, 23,613. We print it again, and we get nothing. Why did we get nothing? Because we moved our head pointer. We screwed up. Because it's not pointing at 1. What ends up happening is we keep moving it until it points at what this points at, And then eventually, I didn't draw it correctly. Eventually, it copies this and it points at nothing. So, yeah, I didn't draw it correctly. All right, don't do it that way. Don't do it that way. If I don't explicitly tell you not to do it that way, there's normally 2 or 3 people who do it that way. So, all right, I've been talking a really long time now. You want to take like a 1 minute break? It's like hot and humid in here today, isn't it? So, all right, stand up for 1 minute, then we'll move on.
What happens if you have if that while loop have the condition where when head doesn't equal no, the while loop ends? Like, what happens if you just have a loop that's just not going to end in this situation?
Well, I'm not quite sure your question. The loop will eventually end because it'll eventually reach something that's null. Now, you can have, if you really screw things up, you can have a list that's not a list, but you end up getting a loop in it. It'll just run forever.
So the program just won't.
If it's not a list, if there's a loop in the list, so that there's a circle and it ends up, which is a possibility, it's possible to do it that way by accident, it'll just print forever whatever's in that circle. So, in fact, one of the questions that sometimes are asked at programming interviews is, how do you detect if you have a loop inside a linked list? So,
That's like a common problem.
yeah. And how would you detect it if it was the case? Like, you don't know if your list is really, really long, so it's just printing lots of stuff out, or if there's a loop in it. So, you what? Yeah, you have what's called a doubly linked list. Yeah, where you have that points to the thing before it as well. Trust me, there's like, I'm not going to say there's infinite variations, but there's. Oh God, yeah. Oh yes, all sorts of trees. Do you remember that try thing I showed you for like? That's all. You have one node that's got 26 pointers, and each of those has 26 pointers. What are you grimacing about? It's awesome. Oh yeah. Oh yes, if you mess something up. Yeah. No. You're looking at what goes wrong. You have to focus on the pride and joy you feel when it all goes right, and you've built something incredibly complex that works. It's awesome. So. All right. So here we are. We're back. We've figured out how to add things to the list. We've figured out to print the list. Let's look at searching the list now, okay? So we'll write a little method for the list class. We're going to call it, anybody have any good ideas for searching list? And I'm just, for fun, going to make this return a bool. And essentially, this will just tell us whether something is on the list or not. It'll say yes or no, okay? That's all we're going to do is, given an int, see if it's on the list or not. So let's go on down here. We'll go below the print list wrong. Oh, we can go below add node. Doesn't matter where. And we're going to say bool. This is a member of the list class. Its name is search list. And it takes an argument as an integer, which is the integer that is sought. Now, given that we have a list that looks something like this, how do we figure out if a particular integer is on it or not? Yeah, and we're going to use a while loop, and how we're going to do it is we're just going to go down the list and look at every element on the list and see if the thing we're looking for is in there. Make sense? That's all we're going to do. How do we go through the list? We know we need a node temp. Node star temp. And what do we set this thing to? Head. What happens if we just use head directly? Bad things. It is doing the wrong way. It is very, very rare, unless you are adding a node to the list or deleting something from the list, to ever manipulate head. If you find yourself trying to do something and changing head's value and you're not adding or deleting from the list, odds are you're doing something wrong. Okay? Just in the general case. All right, so if node star temp equals head, we say while temp isn't null, which means it's still pointing at something. What do we do? If Do I need what? Nope. If sought, if we look, is equal to what? Yep. Temp arrow get data. So what this says is we have some int that is the int we're seeking for. So I named it sought. And what we say is we're going to have a pointer, and this pointer is going to start at wherever head is and go down one at a time. And if at any point the data inside the node that temp is pointing to is equal to what's sought, then we're going to return true because we found something. Otherwise, what's going to happen is if we get to the end of the loop, and we haven't found anything and returned it, that means it wasn't in there. Return false. Okay? So here's what this does. Node star temp, create a temporary pointer, make it point to the same thing that head is pointed to, which means make it hold the same address that it's holding, that head is holding. We say, while this temporary pointer is actually pointing to an object, because if it's not null, it should be pointing to an object, we look and we say, well, if the data inside the thing it's pointed to, temp arrow get data, is equal to the thing that's sought, we're done. We return true. We only had to find one thing to know that it was in there. We return true. Otherwise, if we keep going and we get to the end, and this loop ends because temp is equal to null, that means we never found anything. Because if we had found something, we would have returned true, and the method would be over, so we return false. Yes? Oh yeah, I'm missing something, aren't I? Thank you. Here. It's a big error. All right. And of course, I forgot to do what I always forget to do half the time when I write my own code, is advance the pointer to the next thing. So, except that's not even right. Sorry, I cut and pasted out of the wrong place. How about, that's one wrong here. This one looks good. Sorry about that. Totally screwed that up. All right. And we have to advance the pointer in there. All right, who's baffled? Anyone admit to it? Questions? Should we test and see if this works? All right, what I'm going to do just for debugging, I'm going to put that in just to debug. And what's going to show us is each time we look at one of the nodes, it'll show us which node we are checking. Okay? Does that make sense? Who's with me? Who's against me? How many people are so lost at this point that I could say anything and you just sit there and look at me? No one's going to admit to it? All right. Well, hopefully you can look at this on the video and test it after class, and we'll see what's happening. So we have some nodes. I'm going to get rid of this print wrong because that messes up the list for us. And what do we want to search for? How about 100? All right. So what we're going to do is we say cout. If we do search list 100 on the list, it's a Boolean, and it's true, was found, else, what are we going to print out? Not found. All right. So we have our print, we have our search, and here we go. Let's see if this compiles. It compiles. So when we run it, here's our algorithm. We're going to create a list. We're going to add nodes to the list, 13, 100, 6, and 23. We're going to print the list. When we print the list, what is that going to print out? Print out the same things backwards. Then we're going to start searching for 100. If we look at search for 100, what this does is it says it checks each node. It's going to print out the value of each node it sees. And then when it returns, it's going to either tell us whether it was found or whether it was not found. Anybody have any inkling of whether we're going to find 100 on this list or not? Who thinks we are? Who thinks we are not? All right, let's give it a test and see. So let's run it and see what happens. So here's our print. We print it out backwards, 23, 6, 113. We say searching for 100. It checks the first node. It finds it's 23. Is 23 equal to 100? No, so it goes on to the next. Is 6 equal to 100? Goes on to the next. Is 100 equal to 100? It is if you're using int values, maybe not if you're using doubles. And so that method stops and it says was found. Okay. If we try a different value like 1,000, is 1,000 on there? We'll compile it, clear the screen. When we run it, you can see it checks each node, and then when it does, it says it is not found. Yes? Mm-hmm. Yep. So the way we wrote this search, is it just returns true or false. We wrote it so if it finds it once, it lets us know we're there. If we wanted, we could change it, and we could have, instead of a bool, instead of making search a bool, we could make it an int, and we could count how many times things were there. And we could return 0, but I don't really want to do that. It's possible, right? There's a wealth of things that you can do. It's just a matter of what you want to do. Okay. All right, so who's with me so far? Yes. Who has a question? Any question? Nope, going once, twice. All right, so let's talk about one more thing that we need to know. And the one thing we need to know is a destructor. And the reason is that when you declare something, when we do this call up in the add node or down in the add node, which is around here somewhere, right here, when we say new node, when you use new and you declare something using new, when does that go away? It doesn't. It does not go away. When you use new, it does not go away. And in fact, if we wanted, we could just write something that created nodes and eventually the program would crash. I bet it would take a number of seconds to happen on my computer because we have plenty of memory, but eventually it would run out of room and it would crash. Okay. Should we try that? All right, so let's just see if we can make it crash really fast. All right, so what did I just do right here? Int x equals 0. I declared a variable named x. What does while 1 do? It's always true. And so how often does it loop? This will loop forever. We add the node with the current value of x, and then we increment x. So this is going to start at 0, add a node to the list, 1, add a node to the list, 2, add a node to the list. And every so often, it'll do it. Now, here's what I'm going to do. If x mod 10 million. I'm just going to have it print out every once in a while so that we can know where we are. We'll be able to see how many things we've gotten so far. Okay? Yeah, 10 million might be too low a number. We might have to go to like 100 million because it can store a lot of ints, okay? And the problem is that actually printing out things is slow, and so if we print out every single number, we would probably not be able to let it run long enough. Okay, so it would help if I printed out x. X is going to be 10 million is going to be too high, so I forgot to put the value of x in here. No, don't crash. So you know why it did that? It's because we were filling up so much memory, it had to do some stuff to get the memory back. Okay. All right, ready? So we're just filling up memory with a giant linked list that, as of now, has what, like 100 million nodes on it? Yeah, we could do that. It would crash faster if we made it along. So, I mean, probably we have to, if we did it this way, we're probably going to have to wait for it to count to like, I don't know, 800 million or something like that. I mean, we have a lot of memory these days. So, in fact, I'm just going to stop this because it's kind of pointless to sit here. You can do it and crash your own programs if you want. But, okay, so what just happened now is it didn't crash yet, but now what it's starting to do is there's not enough room in RAM, so the operating system is taking pieces of RAM and putting it on the disk for us and swapping out so that we have, it's pretending we have more memory. So when it paused there, when it pauses like that, what it's doing is it's going, oh my God, I've run out of space, I got to put some stuff on disk. So this is going to run for a while now until essentially it runs out of disk space as well, and then it's crash. So let's just not even dot it. So I'm going to hit Control-C to make it stop, and it's going to take me like a minute or two to get my computer back. Because what it's going to do is it's going to have to go through and unload all that memory. And even though memory is very fast, it's doing it over so much stuff. And now what's going to happen when I switch back to my editor, I'm going to get the spinny beach ball for a while. Am I? No, it's working right away. So it did a good job. Yes? Yes, after the program is done running, it will recover that memory. But while the program is running, it will not ever recover memory. So anything you use with new actually stays until you tell it to go away. Now for us, this isn't such a big problem right now because we're only going to run our program and then we're going to stop. But as you go on, when you create these things, if you're done with them, you need to destroy them. Okay. So that was probably a waste of 2 minutes, but it was kind of fun for me. All right. And I didn't even actually see it crash. It would eventually crash. It says there's an error. It stops running. It's not very exciting. Not very exciting. All right, so the destructor. Let's actually create the destructor for this. What does the destructor look like? And what I want to do first is just show you when this gets called, okay? All right, so all I did is I put a printout there. And this is for demonstration only that we're printing out. And what I'm going to do is say, put a C out right here. Program ending. And we'll run this and see what happens, okay? So compile it. We'll run it. I took out that giant loop. And here's what you see. It creates the list, it prints it, it does a search, it doesn't find it, it ends the program, and after the program ends, it calls tilde list, right? So there's a difference between what you need in this case and what you generally need. In this case, for this class, you don't actually need a destructor or destructor. And the reason is that when our program ends, the computer is going to take back the memory anyway. But I need to teach it to you because you're going to need to know it later, and because you need to know how to make things go away. Have you all seen Disney Fantasia at some point? Right, with the Mickey puppet who creates all the brooms that come marching in, and there's just brooms everywhere, and he can't get them to stop. What I've shown you so far is like how to create a broom, but not how to make it go away. And it's not like the brooms are going to come beat the crap out of you or anything because it's a program, but just you need to learn how to make them go away. Okay, everybody good with that? So here's our list, and it's getting called. So we can see it's getting called. If we have a list like this, how do you think we're going to go through and delete all those things? And I'll just give you a clue right now. The opposite of new is delete. The opposite of new is delete. So we have a new command. We're also going to have a delete command. So anybody have any idea how we can delete each one of these nodes on the list? Yeah? Yep. So what we need to do is we need to loop through the list, just like we've been doing, except each time, instead of printing something out, we're going to delete it and make it go away. And what we have to make sure is at each step, we have the pointer to the next one so that we know the next one we want to delete. Okay? So let's go ahead and do this. Here's what we're going to do. We're going to have a little loop. This is going to work slightly differently. We're going to say temp node star temp equals what? Head, that'll work. Let's actually do this. Let's do head, arrow, get next. So instead of temp starting at head, temp is going to point at the thing that the node head is pointing at. I screwed that up. Instead of pointing at head, it's going to point at the next thing along the list. Then what we can do is we can say while head does not equal null, delete head. Now, I'm doing something here to the head pointer. In general, when you do something to the head pointer, what should happen in your mind? Alarm klaxon should be going off. You should say, uh-oh, I'm doing something with the head pointer. That's bad. Okay? What are the two exceptions to doing things with the head pointer? Adding to the list or deleting from the list. And what are we doing here? Deleting from the list, so that we're okay. So now what we say is head equals, oh, wait a minute. Let's see. Yep. Head equals temp, so that'll advance along. And temp, again, equals head, arrow, get next. Now, because what we're doing, and what I'm trying to show you here is a slightly different approach. Last time, when we talked about printing the list and we talked about searching the list, we had the head pointer and we had a temp pointer that went down the list, right? Everybody with me on that? Now what we do is we're going to have a head pointer and a temp pointer that points at the thing after it, and each one of these is going to move one step at a time. So the temp pointer will always be one hop in front of the head pointer. Okay? All right, any questions? Yeah, so here's what we're going to have. And here's what we're going to have. We're going to have the head pointer that points at the first node on the list, and the temp pointer that points at the second node of the list. And what's going to happen is each time that the head pointer is deleted, the head node is deleted, we're going to reset that. So that the head pointer will always be pointing at the head of the list, and the temp pointer will always be pointing at the second item on the list. But we're going to keep deleting the head. So we're going to have to push these things down one at a time. Yes? Great. All right, so I need 5 volunteers. Raise your hand, please. All right, 1, 2, stand up, come up front here. Come on, 3 more. You're not going to get injured. Come on, it's fun. 3, 4, 5, come up here. Okay, so you two stand off to the side. You 3 gentlemen come right over here. Congratulations, you're node number 5. You're node number 10. You're node number 15. Okay? I want you to point at him. I want you to point at him. I want you to point at null. Use other arm. Okay. So this is our linked list. Everybody good with that? Everybody good with this? Understand we're doing node 1, node 2, and node 3. We need a head pointer. Come right over here. You're going to be the head pointer. Point at the first node. Everybody good with this? So far we good? Great. You're going to be the temp pointer. Stand in front, point at the second node. Awesome. Here's what's going to happen. We're going to delete the first node. Ready? We delete it. Go sit in your seat. Head moves over here, points at that. You go to the next person. Got that? Delete that node. You can go sit down. You move over here. You point at what he's pointing at, which is null. Okay? Delete. You go away. The list is gone. Okay? We had 2 nodes in there, 2 pointers to do that. Thank you very much. Have a seat. Round of applause for volunteers. Did that help you understand? You can say no. Uh-huh. Because if we delete, if the head is doing all the deleting, why do we need the temp? So let's say we have head point here, and we delete this, like that. Where's the second node? How do we get there? You can't. We can't, because we deleted the only pointer to had it when we delete head. So instead, if we have head pointing at one thing and temp pointing at next, like that, then when we delete head, where's the second node? Now head points here. And then we can follow this pointer to point temp over here. Does that make sense? And now when we delete head, we can still get to the rest of the list. Got it? Yes, sir. Delete is the opposite of new. New says, here's the address of an object. Delete says, given this address, go there and get rid of the object. So delete is the opposite of new, the exact opposite. All right, there's a bug in this code. And there's a bug in here on purpose because I want you to see what happens when you have a bug and it causes you to crash. Okay, well, so let me run this and I will demonstrate that in fact there's a bug. And what we're going to do is we're going to put a C out here. I forgot the arrow. I forgot this. All right, so we're about to delete something. All right, so let's run this and see what happens. There's a bug in this, right? I told you that. It should crash if all goes well. Segmentation fault. All right, there's a bug here. And if we look at what happened, the program end, we called the destructor. It said about to delete 23, about to delete 6, about to delete 100, about to delete 13. Segmentation fault. Yes, sir. No. Yes, that's exactly what happened. Yes. So what happens in a segmentation fault is that you're trying to follow a pointer, you use the arrow operation, on something that isn't actually an object. Like you either call it on a null pointer, or you call it on a pointer that's pointing someplace randomly in memory. Okay? So what happened here is we got a segmentation fault because at some point, one of these pointers was null. And the pointer that was null was temp. Because what happens is essentially wait. Let me think about this for a second. I knew there was a bug in there and I had in mind what it was. Oh, what ends up happening is with head right here, head equals temp at some point, head becomes null. And what happens here is when you call head arrow get next, we're calling get next on a null pointer, and that causes a crash. Okay? Now we can fix this. Like that. And this should do away with the problem. So the problem is that at some point we delete head. Head gets set equal to temp, but if temp is null, then the next line when we say temp equals head arrow get next, head is null, and when you call the arrow operator on a null pointer, you get a segmentation fault. As you're writing your program, I expect that some of you will encounter segmentation faults. If you're getting segmentation faults, in general, one of two things is happening. The first thing that's happening is you're calling the arrow operator on something that is null, like we just did here. The other thing that can be happening is you're calling the arrow operator on something that isn't actually pointing at the right kind of node, at the right object. That happens if you forget to initialize your list. Like if you don't do head equals null in the private thing, it can happen otherwise, but that's the most common. So let me just make sure that we fixed our problem here. And we'll run the program. Yay, no seg fault. Okay. No seg fault. All right, questions? How would you use a file? Well, you might want to use a while loop. You could do something like, I'm going to use a for loop just to show you. In fact, let's do this. Let's create a list a different way. And instead, what we're going to do of this, we're going to say int x equals 5, while x is less than 2000, list.add node x, x plus equals 5. So here we're creating a really long linked list. We're going to start at 5, and we're going to go up to 1995. And we're going to add every value in steps of 5 between there. Okay? And what we're doing is each time we just call add node. So if I compile this, and we run it, we say list 2. This is going to generate all sorts of stuff. So, so here we're printing the whole list. And remember, these things come out in reverse order, right? So we go all the way down to all the way down. All right, and then we call search for 100. Is 100 on there? It should be, but it's going to be pretty far down, right? And eventually it got down to, oh, it was actually looking for 1,000. So at 1,000, the program ended, and then it called the destructor, and now it's deleting all that giant list we created. Okay? So remember, all our examples that we've been working with are relatively small in class, but the computer is capable of huge amounts of data. I mean, when we were running things before and I was trying to get it to crash, we got up to like 400 million entries on our linked list, right? That's one for every person in the United States, and we were able to do it on one computer in like a minute. So computers are incredibly powerful. I don't want you to forget that just because we're working on smaller examples. Sometimes, I haven't done it this semester, but sometimes for the projects, I actually write a program that will generate data for you, so that what will happen is instead of being stuck with my data sets, you can generate huge data sets and test your programs on huge data sets, like ones with billions of entries, because your code can handle that. Okay. All right, other questions? So why did I use a while loop right here? The answer was, how do you do this from a file? You read a file using a while loop, don't you? So there's an example of what you can do with a while loop. Your program's going to have to be slightly different than this because there's not a direct add node. You'll have to do something else. So and that's actually probably the trickiest part of the project, is getting the input in. I think. Other questions? We have 2 minutes left. Yes? So I used a while loop instead of a for loop in this instance because he asked me how to read things from a file. And reading from a file, we use a while loop, so I wanted to use a while loop just as an example. We could have used a for loop, but you don't really use a for loop reading from a file. So, yes? Can you have more than the friend functions that I put in? That should be all that you need. I can't think you'll need any more. See you later. That's all you need for those two. Yeah. If you have those two Fred functions, you can do cout star and then the name of the refugee if you dereference it and it'll print. You can do cin angle star whatever the name of the variable is, and it'll read right into it, directly into it. So, other questions? You all look eager to be gone. So, last questions. All right, let's just sit here in silence for a minute. Or you can go, your choice. Have a good break. I'll see you later.